Welcome to Part 7b in the series of videos on the drying of fruits and vegetables. In this presentation we will continue with our examination of the preparation of materials for drying. We have already gone over the outline of Part 7a. In Part 7b we will examine pre-treatments of materials, including blanching. Then we will examine loading the dryer and monitoring the drying process. We'll look at testing for doneness and storing of the dried material and finish up with some summary comments. Not every food material can just be cut into slices or wedges and placed on racks in a dryer. Often a form of pre-treatment is required to maintain quality. There are various pre-treatments which we will look at now. The first of these will be blanching. In order to explain blanching, we need to look at what happens in some fruits and vegetables that causes them to deteriorate after they are harvested. Consider this cauliflower, which we have seen in a previous presentation, and you'll notice that the florets have a creamy white color. After remaining at room temperature for just over a week, the color of the cauliflower changed noticeably. The question now remains is, why did this happen, or how did this happen? The answer is that there are naturally occurring enzymes present in fruits and vegetables that perform a number of functions. Enzymes are really protein molecules that help promote certain chemical reactions. We say that they are biologically active. Unfortunately, some of these enzymes can lead to degradation of the material. The enzyme polyphenol oxidase promotes a reaction that produces brown and black coloration, and this is an enzymatic browning reaction. Fortunately, most enzymes that cause fruits and vegetables to degrade can be inactivated by heating for a short period of time. This heating process is referred to as blanching. Although most enzymatic reactions require the presence of water, it's a good idea to blanch certain materials prior to drying. And I should mention here that even though there isn't a lot of water present in a dry product, there can be enough water to allow enzymatic reactions to proceed. However, they would do so at a much slower rate. Carrots and beans are examples of products that require blanching before drying. In contrast, tomatoes and mangoes do not need to be blanched before we dry them. We can easily show how blanching works by using another natural enzyme present in fruits and vegetables that has no real negative aspects to it. Peroxidase enzymes are produced in plant tissues to break down peroxide molecules that are a byproduct of some of the cellular functions of the plant tissues. If the peroxide levels were allowed to increase, there could be damage to the plant at the cellular level. The peroxidase breaks down the peroxide into water and oxygen, which are harmless. Here we show the breakdown of hydrogen peroxide in the presence of peroxidase enzymes to give us water and oxygen, which is a gas that is given off. If we take pieces of raw material and expose them to a solution of peroxide, we should be able to detect the presence of peroxidase by the bubbles of oxygen that form. We can then repeat this test on blanched product to see if the peroxidase enzyme molecules have been deactivated, and we'll know this has taken place because if the enzyme has been deactivated, there will be no oxygen bubbles formed. So here we have several pieces of beans in a shallow saucer to which we will add hydrogen peroxide solution. So let me trigger this video now. So we're adding the hydrogen peroxide solution, and what you should notice is the formation of bubbles at the end of the pieces of bean that I have put in the saucer. And I think you can see how there's a foaming action, which is actually small bubbles of oxygen being liberated from the reaction of the hydrogen peroxide and the peroxidase enzyme, and that's the formation of the bubbles that you see here. Now we will blanch some pieces of bean in boiling water for several minutes. So here are the pieces of the bean which I've placed in a coffee mug. Then I have poured boiling water over them and stirred them for several minutes in order to deactivate the enzyme, which typically becomes deactivated at a temperature of around 60 to 65 degrees Celsius. After blanching, the product should be plunged into cold water to lower its temperature and stop the blanching process, and we refer to this as quenching. The test for the presence of peroxidase can then be repeated using the blanched beans. After approximately 3 minutes in the peroxide solution, there was no bubbling whatsoever, so rather than showing you a video, I've included this photograph of the blanched bean pieces that was taken after 3 minutes in the peroxide solution. As can be seen, there are no oxygen bubbles observed for the blanched product. This shows that the peroxidase enzyme has been deactivated. Here's the unblanched material, and we can compare that to the blanched material. And of course, it's quite obvious that there are no bubbles around the blanched slices of the beans. Similar results were obtained in other cases as well, and here we see an example of unblanched carrots and blanched carrots placed in a peroxide solution. The one on the left, which was unblanched, shows the presence of the peroxidase enzyme due to the bubbling action. We have used the peroxidase enzyme as an indicator to show what happens during blanching. The enzymes responsible for degradation in fruits and vegetables are generally easier to deactivate than peroxidase. This means that any blanching treatment capable of deactivating peroxidase will deactivate the other enzymes as well. As a closing comment on blanching, we should not confuse the benefits of the blanching heat treatment with using high temperatures to dry food material. Blanching is a controlled process that only takes a few minutes. It is done in boiling water, so the product never has a chance to dry out and develop a case-hardened layer. Most of the other negative aspects of exposure to excessive heat require a long period of time and are more likely to occur when in contact with air rather than water. Now we'll move on to vitamin C treatment. Many of you may have noticed how the flesh of an apple tends to go brown when it is exposed to the air. Here we see how the apple slice on the right has browned after exposure to air, whereas the apple slice on the left, which is just fresh, has a minimal amount of browning. So note how the browning of the apple slice on the right has occurred after exposure to the air for a relatively short period of time. This happens by means of a process where the oxygen in the air reacts with the natural sugars that are present in the apple to create a brown pigment. This is called non-enzymatic browning, and this is quite different from the cauliflower, which brown due to the presence of polyphenol oxidase. Apples and possibly other fruits can brown during the drying process, especially because of the presence of heat. While most of the examples of browning with apple slices I have seen are not all that pronounced, some people may wish to minimize the browning reaction. This can be done by dipping the apple slices into a solution containing vitamin C. Vitamin C reacts with oxygen quite rapidly. It essentially protects the sugars in the apple slices by removing the oxygen that would otherwise react with these sugars. There are powdered materials available that can be mixed with water to create a dipping solution, and here we see powdered vitamin C that can be used in such a manner. However, lemon juice or lime juice can be used just as effectively. All you need to do is dip the slice of material into the lemon or lime juice for a short period of time, as was done with this apple slice in the photograph at the bottom of the slide. As you remove the slices from the lemon or lime juice, you just need to shake off the excess liquid before placing the slices in the dryer. The presence of the remaining liquid on the surface of the apple slices will not lengthen the drying period in any appreciable manner. It becomes part of the pool on the saturated surface and evaporates quite quickly. There are usually no off flavors due to the lemon or lime juice dip, so you don't need to worry about this aspect of the treatment. In cases where longer periods of time are required for drying, it may be necessary to add chemical preservatives to the material. This is often the case for sun drying of tomatoes in the open air, which can take up to 1 week or more. Chemicals such as sodium metabisulfite can be added as an antimicrobial agent. And before you panic, let's explain this in a little more detail. What will happen is that the materials that are left out to dry in the sun will go moldy unless they are treated. So if we add a preservative to them that contains sulfur, this will reduce the level of mold growth significantly. Sometimes the tomatoes are conditioned by exposing them to sulfur dioxide gas. This produces a preservation effect similar to that obtained by dipping the tomatoes in a solution of sodium metabisulfite, and that's because the sulfur dioxide actually dissolves in the liquid component of the tomatoes and forms that sulfur-based preservative. The use of chemical addition is something that is best left to the experts, so we'll not go any further with it here. Consumers dislike chemical additives of any kind in their food, so it's usually a good idea to try to avoid them. Now let's move on to pre-cooking. Pre-cooking as a pre-treatment depends on the material being considered and its end use. You may wish to pre-cook yams and dry slices of them for later use. Cassava is also something that you should consider cooking. Most of the fruits and vegetables that we typically dry do not require pre-cooking. However, they may require blanching. Pre-cooking will gelatinize the starches that are present, which means it will make them go rubbery. Another example of pre-cooking is to cook rice in water to fully hydrate the kernels and gelatinize the starch, as well as plumping up the rice kernels when they hydrate. The cooked rice can be dried to create an instantized rice product that will have a convenience feature when it comes time to use it. Now we can look at checking as a pre-treatment. Berries often have waxy skins which are designed to retain moisture, as we have discussed in a previous presentation. This makes water removal extremely difficult in the drying of whole berries. Checking offers an alternative to cutting the berries or mashing them to facilitate drying. What the process involves is exposing the berries to boiling water for several minutes, so it's much like a blanching process. This creates small cracks in the skin of the berries, which can then allow moisture to escape during drying. However, the cracks are very small, so the rate of water removal is correspondingly slow. It should be noted that checking is not as effective as actually disrupting the skin of the berry by cutting the berry or mashing it. Loading the dryer is the last step in preparing the materials for drying. We will assume that the dryer design is correct and that it is operating well. We will also assume that the flow of air is adequate. That means it's got the proper temperature and a suitable velocity, and that the direction of the air is across the surface of the material. If all of these conditions are met, loading the dryer is really quite simple. The drying racks can be removed from the dryer and placed on a table or other support for loading, and slices of the material to be dried can be arranged in a pattern to maximize the amount on each tray or rack. The slices of material should not overlap nor touch each other to any great extent. If the material tends to shrink during drying, there is no significant problem in having a small degree of touching, especially in the case of round slices, and I've shown that here, As you can see, we have a minimal amount of touching at the edges, and as the material dries and shrinks, there will be an opening of this, so the effects of the touching surfaces will be minimal. For dryers, where there is an upward or downward flow of air, there needs to be spacing between the slices to allow air to travel through the dryer. This is not an efficient approach to drying, and airflow across the material is preferred due to its higher efficiency. So here we see the flow of heated air across the top and bottom surface of this material as represented by the orange rectangle. If the pieces of material are too small for the open mesh on the drying racks, it may be necessary to use a layer of smaller mesh or screening on top of these racks. In the case of carrot slices, they may shrink during the drying process and fall through the mesh as the drying progresses. Banana slices become quite sticky when they are dried. Using a plastic mesh makes it easier to remove the dried banana slices from the drying rack. So here we see some banana slices on a plastic mesh, and you can remove this sheet and bend it so that the banana slices actually come away fairly easily rather than becoming very highly attached to the metal rack that's underneath supporting this plastic mesh. And please note that these banana slices are thicker than recommended, and that's because this was part of a drying study to determine the effects of thickness on the rate of water removal. Typically they would be 5 to 6 millimeters or 0.5 to 0.6 centimeters thick. A plastic mesh or screen is also required when cooked mashed materials such as yams or cassava are dried. On the left photograph we have cooked mashed cassava before drying, and in the photograph on the right you can see the same cassava after it has been dried. And you can see that the plastic mesh has kept this material from falling through the more open structure of the wire mesh underneath. Now we need to worry about monitoring the drying process. It's a good idea to check the progress of your drying at regular intervals. You may need to rotate the racks in the dryer every few hours if the drying is not completely uniform, and sometimes this can happen even in the best of cabinet dryers. You may also need to shift trays from the top of the dryer to the bottom or to the middle if there is unbalanced drying from top to bottom. In cases where you have mashed product, it may be necessary to stir the bed of material periodically to ensure that the center of the bed is exposed to the drying air. When you suspect that the drying process is nearing its end point, increased monitoring is recommended to prevent over-drying. Over-drying can cause your material to go crispy or to darken in color. And I've shown some commercially dried mango slices in this photograph. You can see by the darkened color indicated by the red circles that some of this material has been overly dried. Now we need to look at testing for doneness, and the question always arises, is it done yet? In part 3 of How Drying Takes Place, we looked at how to determine whether or not a material had reached the end point in the drying process. This information is being repeated here for the sake of completeness. Knowing when to stop the drying process is a question that arises as soon as you put the material in the dryer. Unless you have the appropriate instrumentation in place, you cannot be absolutely certain when to remove the material from the dryer. However, it is possible to make some very good approximations or estimates. In a laboratory setting, we can monitor the process quite closely and predict when the material will reach the target moisture content, which is usually 10%. As mentioned in the previous slide, for small-scale operations which are not equipped with the same monitoring devices, this is a bit more difficult or a bit more challenging. Experience is the major factor that will help you. If you dry the material at a moderate temperature of 50 to 55 degrees Celsius, you should be able to predict the endpoint based on the texture of the product and your own personal experience. Usually, the final product will feel dry to the touch and have a leathery texture. The product, such as dried mangoes, will be pliable and bend easily without cracking. If the dried material is too dry, it will become brittle and crack when it is bent. A visual inspection of the color and other features can assist you once you know what a satisfactory end product looks like. Taste testing of the material will help as well, but let the product cool down for a few minutes before checking it. This is because warm products tend to be soft and can give you a misrepresentation of what the texture is actually like. Another look at the graph for the drying of mangoes will give us a good indication of how long the drying will take. We will also consider this approach when we consider mango and tomato drying in more detail later. So here is the graph for drying the mangoes. On the vertical axis we have the weight of the mango slices in grams, and we're starting at 240 grams, and this graph should be familiar to you. In a previous presentation, we calculated that the weight of solids present in this mango sample would be equal to 33.3 grams, and that's indicated by the dashed line across the bottom of the graph. And you will notice how the green line approaches that dashed line, and it would touch the dashed line if all of the moisture was removed. The shape of the graph shows us when moisture is being lost. As long as the graph is moving downwards to the right, we know moisture is being removed from the mango slices, and this is because the weight is decreasing and the only thing that we're losing in the process is water. When the curve begins to level off, we know that we are nearing the end point. The end point from this graph would be at about 11 or 12 hours. Based on the graph in the previous slide, as we have said, about 12 hours would be needed to dry the mango slices under the conditions that were used in this trial. Your times will vary, but you should expect a time of around this value. Perhaps it may be longer or it may be a bit shorter, but you should be examining your product as you get close to this timing in the drying run. Once again, this is something that you will learn by experience. If you have suitable equipment for monitoring moisture levels, the situation becomes quite easier and a lot of the guesswork is removed. Now let's look at the storage of dried materials. The important thing to remember about storing dried materials is to protect them from moisture. This begins as soon as you take them out of the dryer. Generally, the product that you remove from the dryer will be warm, and that's because the air in the dryer is in a range of about 50 to 55 degrees Celsius, so that will be the temperature of the slices of product you remove. As the product cools down outside the dryer, it can pick up moisture from the surrounding humid air. This is rather difficult to prevent, but you should be aware that it does happen. So here we have the warm, dry product that's cooling down, but as it does, the humidity in the air is attracted to it, and it actually takes up moisture as it cools. Do not package the product before it has cooled down, however. That's a temptation. A lot of people think that rather than have the material absorb moisture from the air, they will put it in a closed container and prevent that from taking place. However, what does happen is that warm product tends to sweat when it's placed in a closed container, as small amounts of moisture leave the surface. This can happen even at low moisture levels of 10%, where small amounts of moisture are leaving the surface of the material and going into the air in the closed container. This moisture can condense and create conditions that are suitable for mold growth inside the container. Once it is cooled, you can then place the material in a clean closed container with a good seal. Plastic bags and jars work well for storage as long as they do not allow moisture and air to reach the product. And we also have to be careful of the air because it contains oxygen, which can participate in a number of reactions that lower the quality of the material that you have dried. Don't forget to label your products properly and have a code or other method to link the production data to each package. So the important thing is here that production codes are a definite must. The packaged product needs to be stored in cool, dry surroundings, out of sunlight and away from pests. Your inventory of material needs to be managed to avoid being held for excessive lengths of time, and you need to remember that spoilage or quality degradation is time dependent, so you must minimize the amount of time that you hold on to a product. Remember the word FIFO, first in and first out, and that will help you keep your inventory moving. Conditions that apply to storage also apply to conditions during distribution and marketing of your product as well. Don't subject dried materials to excessive heat, humidity, and sunlight as you transport them, nor at their point of sale either. So in summary, in this presentation we have covered a great deal of material which you may find has contributed to a degree of information overload. It's true that there is a lot to remember and consider when drying food materials. A good approach is to start small and experiment with drying a certain material. Keep accurate records of what you do, and learn from your failures as well as your successes. Once you have become more comfortable with operating a dryer and doing all the associated tasks, then you can expand your scale of operation or increase the number of materials which you dry. As you conduct your drying activities, you need to resist the temptations to take shortcuts and do things like using excessively high temperatures. Please keep in mind that there are many cause and effect relationships involved, so you should be continuously asking yourself, if I do this, then what will happen? Thank you very much.